Hello Raiders, this is Ms. Prado with video notes for naming binary compounds. We're going to be using the handouts from class glued into your journals so that we can still do a modified Cornell Notes format where you can write questions on the left-hand side, and we'll be writing notes on the front of this sheet, we'll be writing notes on the back of this sheet, and I'm going to be looking for, as part of our grade for taking notes for homework, I'm going to be looking for that summary at the bottom of the page here, on the lined page. 3 to 5 complete sentences is all you need. Just a summary of the concepts here. What I'm also going to do is address a misconception that we noticed on the last test that we took. It's the atomic radius trend. So I'm going to need to see this also, because we need to make sure that we are understanding the atomic radius trend and what that's affecting, because that will actually have some connection to what we're talking about with bonding. All right, so the atomic radius trend. You're going to need to, at some point during this video, pause this and sketch this. We have a really good grasp, looking at our test data, we have a really good grasp on how atomic radius increases as we go down a group. So this is group 1A, hydrogen, lithium, and sodium. And if we're looking at the atomic numbers, hydrogen's atomic number is 1, so we have only one energy level, it's in the first period, 1 electron. It also only has 1 proton in the center. And that 1 proton has a pretty strong pull on that electron because there's nothing in between them. Lithium has an atomic number of 3, and it has a really strong pull on this first level of electrons, but it's in the second energy level, so we have a second level for electrons and that 1 valence electron. It has a weaker pull on that outer shell because it's farther away from that nucleus, but that nucleus has 3 protons. 1, 2, 3. Sodium has atomic number 11, so it actually has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 protons there in the center. It has a very strong pull on this first shell of electrons. It has a weaker but still strong pull on the second level because it has 11 protons. But that very outer shell is farther away from the nucleus, so it's not going to have as much of a pull on that. It's going to be a lot easier for this to float out into space and to actually leave. So this atomic radius is larger. What we're seeing here is if we remove that 1 shell on the outside, that 1 electron, we will have a full shell underneath for sodium and a full shell for lithium. Lithium is small, it only needs 2 in the first energy level. When atoms lose electrons, the protons don't change, remember, because the protons are in the center. So if I have, let's say lithium has 3 protons, it starts off with 3 electrons, but if we lose 1, 2 electrons, together that gives us a charge of +1. Sodium has 11 protons, starts off with 11 electrons, but if we lose that one to get this full valence shell underneath, then we have 10 electrons, 11 pluses, 10 negatives. That gives us an overall charge of +1. So again, +1. So that's where we get that everything in group 1A is going to be a +1. Okay, so we covered that. That's just a reminder. And we get that pretty well. What we tend to get confused on is as we move across a period. For example, sodium is in group 3A. It's in the third period, moving across. So there are only 3 energy levels, 1, 2, 3, 1, 2, 3, 1, 2, 3, for everything in that same period. However, we do have an increased number of protons and electrons. Look what that does. If I have 12 protons pulling on 12 electrons, that's a much stronger force than the 11 and 11 that we started with on sodium. If I am looking at aluminum over here, and I'm looking at 13 protons pulling on 13 electrons, we still only have 3 energy levels, but these guys are pulling on each other more because there's more of them attracting each other with those opposite charges. So aluminum is actually going to be smaller. It's going to be pulled in closer to the nucleus, smaller than magnesium is, because there's more attraction between this nucleus and that outer level. The same thing is going to hold true for everything else in that period. This is the trend that we need to see. As atomic number increases across a period, that stronger proton pull of the nucleus is going to draw that third valence shell in. Okay, so what I need to see is that the atomic radius trend, sketch this in your journals, and then write that the atomic radius decreases across a period. We got that it gets larger as we go down a group because of the added energy levels, but we also need to see that it decreases as we move across the period. Okay? And the other thing that we need to get from this is we said that everything in group 1A is going to have a +1 charge because it gets rid of that one electron, that one valence shell. Well, let's look at sulfur. Sulfur is in group 6A, which means it has, here's our shortcut, it's in group 6A, so it has 1, 2, 3, 4, 5, 6 electrons in its outer shell. So it has a choice. It wants 8. That octet would fill that valence shell. And so it could either add in 2 electrons, or it could take the energy to push away 6. Well, which is more energy efficient? To only have to move 2. So what it will do is it will add in 1, 2 electrons. Maybe it took some from some nearby sodium atoms. All right, so starting off, sulfur had 16 protons and therefore 16 electrons. But when we added these two, we made that 18 electrons. So if I have 16 pluses and 18 minuses, that means I have an overall charge of -2. So guess what? When sulfur forms an ion, it's a -2 ion. It becomes sulfide. Okay, so that means that everything in sulfur's group is going to have that same ionic charge, just like sulfur. So what I need for you to do is to go back to your first page, and we're going to make this easy. We're just going to write this so that we can remember everything in group 1A is +1. Remember that everything in group 2A is +2. We're going to skip the transitions because they can transition between different charges. The transition metals in the middle, we can't always tell exactly what they're going to be. We'll talk more about the transition metals later, but for now, let's just simplify it. +1, +2. Boron's group is +3. Carbon's group is going to be ±4 because they're right in the middle. 4 is right in between having to gain 4 or lose 4, so they actually tend to form covalent compounds. All right, when we get to nitrogen, it's group 5A, so it has 5 valence electrons. It's actually going to want to gain 3. That's going to be the easiest thing to do. We just saw that sulfur is going to be -2, everything in its group, -1 for group 7A, and then the noble gases is 0. Right? And so if you think about it, it makes sense because we're seeing that the groups that are going to attract electrons and therefore form negative ions are the ones that have a higher attraction for those electrons towards the nucleus. So the more electronegative an atom is, the more likely it's going to form an anion, a negative ion. Okay? All right. Okay, so I am going to stop this part of the notes here and start a new video because I'm running out of time on the segments that I can record. So make sure that you have this down. You don't have to do your summary yet. Finish the actual notes on these sheets and then do your summary. Okay, so this is going to be part 1 for naming binary compounds. Now let's continue on for part 2.